In this video, we are going to wrap up our discussion of section 13.5, that is the chain rule multivariable functions. We are going to use this idea to extend, to help us with implicit differentiation in the end here. So take a look. We have some surface. We're gonna derive a formula here. Some surface dependent on x and y, where y is some function of x. All right. So, and I use that formula. Partial of w is the partial of f, and notice this is just the formula that we just talked through in the last video. When I do this, though, I get this like special thing here, dx partial of x over partial of x. That is exactly how we would think, even though, you know, this is not formal way of thinking about this stuff, but I can let that be 1, right? It makes sense that it would be 1. So we have that formula now, and what I'm going to do is set this equal to the 0, and we're going to solve for dy dx. So if I solve for dy dx, right, I got that still times the partial of that, and I would subtract partial of f over with respect to x, and then I would take that and I would divide, so we get dy, not partial, dy dx is equal to negative, okay, that's the partial of f with respect to x divided by the partial of f with respect to y. This formula is big. It's huge. Makes the whole finding our derivative of an implicit differentiation problem much simpler, because we can just find a partial of x and a partial of y and divide them. Let's get an example of this. So check this out. It's much quicker than what we're used to. I have the formula there. So to find that, I'm going to find the left side. I got to have it equal to 0 like it is. I take the partial of that with respect to x. I get 4x plus, okay, the 1/2 comes down. I get 3/2 xy to the negative 1/2 times the partial derivative of xy with respect to x, which is y. Minus 2y is gone, minus 4 is gone. The same equation with respect to y, I got 3/2 xy to the negative 1/2. This was gone, right? No y. Times the derivative of xy with respect to y, which is x. Let me fix this 1/2 here. It's like really gross. There we go. So if I want to find dy dx, I just take that top function. Let's clean these up. Maybe we can make them better. 4x plus 3/2 xy to the 1/2. This one is 3/2 x squared y to the negative 1/2. Okay, so this is going to be negative. The x goes on top. And then we got to be really careful here. One sec. No, we're good. Okay. So I put 4x plus 3/2 x to the y to the 1/2, and I divide that by 3 over 2 x squared y to the negative 1/2. And we could fix this in a certain way, right? Flip things around and stuff like that. That should be there. Oh, actually, I think I messed up here. Okay, go back up here. That negative 1/2 goes to both of those. So let's do it 3/2, and then we get x to the negative 1/2, y to the positive 1/2. There we go. All right, so we got 3/2, x to the negative 1/2, y to the positive 1/2. There we go. So now we have a formula there. You can reshape this if you want. Doesn't really matter. We could multiply both top and bottom by 2 to make it cleaner. I guess we could do that. Let's clean it up a little bit. So I'm multiplying everything by 2. I got a negative 8x plus 3 times the square root, and that's all jacked up there. But let's leave it the way it is. And then over, I multiply that by 2 as well. I get 3x squared y to the negative 1/2. It looks a little better. But anyways, we have a quick way to find the formula for our derivative given an implicit formula, one that we can't solve for y. All right, let's get one more example of this in. But let's talk about if it was a function of 3 variables, x, y, and z, instead of 2. How we would do this is we couldn't do the partial. We'd have to pick what we want the partial with z to be. Well, we could grab this, the third variable with respect to x is this way, y is that way. I'm not going to prove or anything or go through the reasoning for that, but we're going to work one more example. Yours may not say this. It's not what I wanted there. I want this example, x squared plus xy minus x squared z plus y z squared. Your notes should have that, unlike mine. All right, so the partial, I need partial of z over x. How this goes, it's always negative f with the x there, and then the other one z. The other one, when we get there, partial of z with partial y, it's always the partial of y on top over z, whatever the variable is that we're trying to respect here. Take the partial of, not with respect to. Okay, so I get negative, and then I just take each one of these. Okay, I got 2x plus y minus 2xz. That's it on top. On bottom is with respect to z, so I get negative x squared plus 2yz. So there's a good answer. That is the partial of z with respect to x. So it actually even can make this a little quicker for us. Now I do it with y. So I get x plus z squared. That's the partial with y. And then the partial with z, it's the same thing, so I'm just going to write it again. So this formula can be extremely helpful if you can remember it. This is one I think I would put on a note card or some kind of sheet of paper to remind me that this could be a very quick way to find a partial derivative.